Okay, dear colleagues and audience, okay, it's time for our lecture. First of all, thanks our audience to attend tonight's online lecture on logic and the foundation of mathematics at Wuhan University by Dr. Juan Aguilera. Okay, first of all, it's my pleasure to introduce the speaker tonight. Here is his picture. He's very young, and up to now, he should be the youngest speaker at our online lecture series on logic and foundation mathematics. Education. He got his PhD in mathematics in 2019 from Vienna University of Technology. And he got his bachelor degree in applied mathematics in a university from Mexico. Current positions, he has several positions. He is a project leader at the Institute of Discrete Mathematics and Geometry of the Vienna University of Technology. He is also a postdoctoral fellow in the Department of Mathematics of Ghent University in Belgium. Also, he is a guest researcher in the Faculty of Mathematics of the University of Hamburg in Germany. Research areas, he has a wide research interest in a lot of areas. Also, is one of the few people who work on all four main fields of mathematical logic. His publication include the following areas: truth theory, set theory, recursion theory, model theory, non-classical, mainly valued, and model logic, as well as interactions between these areas. Awards. He has won several awards here. I just mentioned several ones. In 2022, he was offered the Best Paper Award, which is awarded by the Faculty of Mathematics and the Information of the Vienna University of Technology to the most outstanding article written by our faculty member in 2021. In 2022, he was offered the Dissertation Award of the German Society for Mathematical Logic and the Foundations of Exact Science for the most outstanding PhD dissertation in 2018 to 2022. In 2021, this is the names of award, which is awarded by the Austrian Mathematical Society to the most outstanding dissertation to mathematics. Also in 2022, he got the EW-based dissertation prize awarded by the Association for Logic, Language, and Information to the most outstanding dissertation in the area of logic, language, information, and computation worldwide. So definitely he's a young talent. And we first meet during the international conference. And whenever he meet new people, he's very energetic to discuss the questions with other people, just like what we are doing, what is the problem you are working on, what is the open problem in your field, this kind of question. So it's very impressive. Okay, that is the brief introduction for the speaker. Okay, we invited some colleagues to attend, but unfortunately, due to the time conflict, they cannot attend this lecture to act as the interlocutor. But every audience is free to ask questions after the main lecture. And then we have around 15 minutes for audience to post your question if you have. Okay, now it's the time is for the Dr. Juan Aguilera for his lecture on Soundness Spectra. Please and welcome.
Thank you. So I'll share my screen, but I'll do it from my other identity. Okay, so it should be working. So let me know if there are any problems with any technical problems. So I think if everything's okay, you should be able to hear me and you should be able to see my screen.
Yes.
And you should be able to see I will be writing. And so I think the plan is, because I don't have a very clear notion of what everybody knows, so I'll tell you some things, and if at any point anybody has any questions, just ask questions, and then we can look at those, we can digress. Everything's possible today. So the first thing I'll start with is the title, which is Soundness Spectra, with a particular focus on I12. And that's going to be the topic for today. And the story begins with the world of ordinal analysis. So there is a notion, which if you haven't seen before, you'll see it now, which is that of the pi11 norm of a theory. So let's define it. Okay, let T be a theory. And for today, all theories are recursively enumerable and extend ACA 0. They don't have to be in the language of second order arithmetic, but they have to be in some language that can interpret arithmetic. So these are nice theories, like they can interpret PA, and they extend ACA 0 in their interpretation of PA. So T could be ACA 0, could be Z of C, could be some other thing. And then we define the pi11 norm of T is the supremum of all ordinals alpha, such that alpha is isomorphic to R for some recursive, well, it's going to be a world ordering, but for some recursive relation, let's say, binary relation on the natural numbers, such that T proves R is well-founded. So T interprets arithmetic, so it can talk about well-foundedness, and it can talk about some binary relations on the integers being well-founded. And in the real world, these will actually be isomorphic to ordinals. So we just take the supremum of these ordinals that T can talk about, and that's the pi11 norm of T. And the first example of this, if you haven't seen this, is due to Ghent. So the pi11 norm of PA, which is the same as the pi11 norm of AC 0, is called epsilon 0. And this is an ordinal which is defined as the supremum of omega, omega to the omega, omega to the omega to the omega, and so on. So we have epsilon 0 is the same as omega to the epsilon 0. And it's the least ordinal with this property. And Ghent obtained this fact as a side effect of what he was really interested in, which was proving the consistency of arithmetic. This was from Gensen proof of con PA, or is. So Gensen showed by induction on epsilon 0, PA is consistent. And the induction it's a very simple induction. It's a recursive induction. Let's say pi1 induction. And so then the question became, can you do this for stronger theories? Question, can this be done for other T? So at this question, lines are very thick. Oh, you of looking at go in a different direction. So let's focus on this notion. And the idea is that the pi11 norm of T can be seen as a measure of the true pi11 consequences of T, because it's talking about which ordinals that really are ordinals T can prove are ordinals. And ordinals are pi11 complete, so in a way this is measuring how much pi11 T is aware of. And what I would like to, the first thing I'd like to explore today is whether we can do something similar for pi12. So 2 questions. Define a similar norm for pi12, or maybe 2 goals. And the second one is recover an ordinal valued measure of the true pi12 consequences of T, just like we had for pi11. So, and we will see that actually this can't happen. So the point is that, well, ordinals are pi11. So if we want to capture pi12 consequences of T, we can't be talking about ordinals. We need to talk about some other thing. So this object here will not be an ordinal. It would be some object which is more complicated. And then this means that this ordinal valued measure, well, that can't exist, because the measure that we can expect to get will be some other type of object. And this is going to be a problem because ordinals are linearly ordered. So this lets you impose a linear preorder on theories, or on pi11 sound theories. And this type of object will not be linearly ordered. So we will have an order in theories which is not linear. So if we maybe want to weaken this to a linearly ordered measure of the true pi12 consequences of T, this can't happen. But what we can hope for is the dual part. So the false sigma 1,2 consequences of T. Sorry. The true the false pi12 consequences of T. which is like, yeah, so we will measure the strength of T and how hard it is to falsify some incorrect consequence of T. That's like the dual thing. And we can try to obtain this. Yes? Is there a question?
Oh, you say some people join in and he forget to close his volume.
Oh, I see. I thought it was a question. Okay, so then this is what we want to do. And this thing is going to be called O12 of T. And I really wanted to talk about this, but this definition kind of comes along the way. So the first obstacle, and it is a good point to mention that unless mentioned otherwise, from now on, everything is joint work with Piotr. So I mentioned this obstacle, which is that this type of object cannot be an ordinal. If we really want to measure of the consequences of T, of the pi12 consequences of T, which works exhaustively, we need to be talking about some type of object which is pi12 complete and not pi11. So it will be a type of object called a dilator. So I'm not sure everybody here knows what that is. So I would say what that is. But if everybody knows what this is, I can skip it. So a dilator is a type of functor on ordinals. Let's maybe be a bit more precise. So or actually, let's just look at well orders. Well orders can be viewed as a category. Where morphisms are functions f from A to B, which are strictly increasing. And this becomes a category. The objects are, of course, well orders. And if you like abusing notation as much as I do, you'll just call these ordinals. And then dilators are functors on well orders. So for every A, which is a well order, D of A will be a well order. And if you have a function which maps A to B, D of F will be a function which maps D of A to D of B. So here you have A, and maybe here you have B, and maybe this is F. And then here you'll have D of A. Here you have d of b. And d of a will get mapped to d of b via d of f. So that's a drawing. And yeah, everything commutes. So that's the first condition. It's a functor. It's not any functor. Properties in it. So we'll have two restrictions. And I would say the first one is more important. It commutes with direct limits. So suppose you have a system D of well orders. And this system is directed. And it has a limit. Every directed system has a limit. Let's call it alpha star. And these are morphisms. Then you can think of this is a curly D. You can think of a image system where you take the images of everything. And this system also has a limit. And condition number one says that this limit will be precisely D of alpha star. And moreover, these direct limit embeddings will be precisely the images. And the very if we have a directed system where ordinals are just initial segments of the next ones, and the embeddings are all the identity, then, well, these will commute. But D might not preserve identity. So it doesn't mean that D of gamma, let's say gamma is the limit of gamma I. It doesn't mean that D of gamma will be the limit of D of gamma I. Because D is any functor, it might not map the identity to the identity. There's nothing special about this example. There was really no reason to bring it up. And condition number two is that D commutes with pullbacks. So maybe let's not say much about this for now. I don't know that this gives much intuition. So I think this is enough of the definition for now. So that's a dilator. A dilator is a functor on well orders satisfying 1 and 2. And the reason why I wanted to emphasize 1 is because there's a nice consequence of this. So D commutes with direct limits. Now, if you take any ordinal, you can write it as the direct limit of the directed system of all its finite subsets, where the embeddings are just inclusion. So if D commutes with direct limits, and we want to know what D of alpha is, we can take alpha. So we can take alpha. Let's say alpha is an ordinal. And then look at all the finite subsets of alpha. And then these form a directed system where the embeddings are given by inclusion. So then we can look at the image system. Where we take each of these finite subsets and then we expand it. Let's say this is A. Now we have D of A. And we look at the inclusion here and see what this is. And now we have a new direct system. And by commutation with direct limits, the limit of this system will be precisely D of alpha. So if we know what D does to every finite order, and we know what D does to every finite morphism, then we can reconstruct what D does to every ordinal. So even though D is a proper class, it's coded by a set sized object. And then if D of A, D of F are countable for a finite order and F finite morphism, then D is coded by a real. So we can use the language of second order arithmetic to talk about dilators. By the way, an example I could, if you know a little bit of set theory, we can view a real X sharp as a dilator. So take alpha, so take any well order, it's isomorphic to an ordinal, and it's going to get mapped to, let's call it C alpha, which is the alpha indiscernible of L of X. And suppose we have a function from alpha to beta. To take an ordinal, we want to define d of f, which is a function from the alpha indiscernible to the beta indiscernible. We'll take any ordinal in the domain, c less than the alpha indiscernible. So it can be written as some term that involves x and some smaller indiscernibles. For some term in the language of set theory involving x. And some number k and indiscernibles. Then d of f applied to c is we just take the same term, but replace the constants according to f. We shift them according to f. So f maps to elements of beta, and it's order preserving. So this will define some ordinal in L of x, and it doesn't depend on which term you chose by indiscernibility. So this is a well-defined map, and well, you can check that it's a dilator. So that's an example which is of no consequence to the rest of the talk. So where was I going with this? We can talk about dilators as real numbers. Some dilators, namely countable dilators, dilators that map countable things to countable things, or equivalently finite things to finite things. Sorry, finite things to countable things. And then the collection of codes of dilators is pi12 complete. This is a theorem of Girard. And so why is this? I guess talk about dilators as real numbers because countable dilators are coded by countable things, just by real numbers. But it's not straightforward to tell whether something that might be a code of a dilator is actually a code of a dilator. Because in order to say that something is a dilator, well, you have to say that it's some object that satisfies all these algebraic conditions. 2, for example. It's something that looks like a dilator. This is called a pre-dilator. But then you have to say the important condition, which is that for every x, which is a well order, d of x is a well order. And this is pi12. And it's pi12 complete. That's the theorem. So this is a nice type of object that is in spirit close to ordinal numbers. You can maybe think of it as a generalization of ordinal numbers to a higher type. And it's going to be, yes? Okay. So this is a natural type of object, which is pi12 complete, and we can generalize many facts about ordinals to dilators. So this is what we're going to use. And then we get to the definition. let T be an RE extension of, let's just say, elementary comprehension. The pi12 norm of T is defined as the least dilator D such that whenever T proves that F is a dilator, we have F embeds into D. Okay, so let me say, I guess I haven't defined what embeddability is. So let's talk about that. And then we'll go back to the definition after this. A specific definition to dilators, the point is that these are functors. And there's a natural type of morphism that you can define on any type of functor, which is called the natural transformation. So embeddability is given by natural transformations. So a transformation from F to D consists of a family of morphisms, T sub A, for A well order, where T of A maps F of A into D of A, and whenever we have a function from A to B, so what can we do? We have F of A, we have F of B, and we know that F of F maps the one below to the one above. And we also have D of A, and we also have D of B, and we know that D of F maps the one below to the one above. We know that this one can go to the right via T. This one can go to the right via T. So what we want is that this diagram commutes. So a natural transformation from a dilator to another dilator, it's like any functor. So you point-wise map one dilator to the other in a way that commutes. This is called naturality. So this is the notion of embeddability for dilators. And so what we're saying here, the pi12 norm is the least dilator D, such that any T provable dilator embeds into D, and that's it. And what does least mean with respect to embeddability? So this is saying the following. Suppose you had another dilator D prime such that all the T provable dilators embed into D, then sorry, let me draw this again. Such that these all embed into D. Then the pi12 norm of T would also have to embed into D. And if you think about the definition for ordinals, because the pi11 norm of a theory is the smallest ordinal such that all the provable well orders of the theory embed into it. So what does that mean? That if you have any other ordinal so that all the provable ordinals of the theory embed into it, then the pi11 norm is smaller, so it embeds into it as well. So in a way, this definition extends the other one. What is not clear, not immediately clear maybe, is whether this exists. Because for ordinals, they're well ordered. So any class that is non-empty has a least element, and that's how you get the pi11 norm. But dilators are not well ordered or linearly ordered. So it's not immediately clear that this object, according to the definition, would exist. But we showed that it does. So we showed that, suppose that T is pi12 sound, then the pi12 norm of T exists and is recursive. And now you can ask all kinds of questions. You would ask about pi11 norms, but you can ask them about pi12 norms. And what I wanted to look at is what could happen if we get rid of this hypothesis. So let's maybe have a short digression to remind ourselves. Suppose that T is not pi11 sound, then the pi11 norm of T is always omega1 ck. So regardless of what T is, and then there's not really anything interesting to say about it, because all the pi11 unsound theories look the same from the point of view of the pi11 norm. And that's where the story ends. So is this the same thing for pi12, or could you say something interesting about theories? So suppose you take T is a pi12 unsound theory. So for example, how about something like Z of C plus there is no transitive model of Z of C plus there is an inaccessible. So this is a pi12 unsound theory. And if you were just doing ordinal analysis, well, maybe this is too complicated for ordinal analysis, but what about this? If you were just doing ordinal analysis, then it wouldn't seem like an unsound theory because ordinal analysis only looks at pi11 consequences. You would just do the usual thing and conclude that the pi11 norm of t is epsilon 0. But the pi12 norm of t is not defined. And so you have this interesting mismatch happening here. And then you might ask if there's any kind of interesting proof theory you can do with pi12 unsound theories, other than just the ones that are trivially pi11. And this leads us to the definition of the pi12 soundness ordinal. Let's separate here. So suppose T is pi12 unsound. Then there is it meets and proves a pi12 consequence, which is not true. But by completeness, this pi12 consequence is of the form D is a dilator. So T extends AC0 was part of the rules of today. So it knows that dilators are pi12 complete. So there's a pre-dilator D. So a pre-dilator is like a dilator. It's like a potential code of a dilator. It's an algebraic object which satisfies functor on well orders, which satisfies these conditions 1 and 2. But it might not be a dilator. We don't know that because it might not preserve well-foundedness. So it might map. So it's not a functor on well orders. It's a functor from well orders to linear orders, or a functor on linear orders. And if it maps well orders to well orders, then it's a dilator. And if not, then it's not. So by completeness, we can find some pre-dilator D such that T proves D is a dilator, but D is not a dilator in reality. So what does this mean? This means that there is an ordinal alpha such that T of alpha is not well ordered. The least such alpha is called the O12 of T. So this is the pi12 soundness ordinal of T. And now this is an ordinal. And the intuition was that just like the pi11 norm is a measure of the pi11 consequences of the theory that are true, and it's a linear measure, so you can always, it's a pre-well ordering on theories. The pi12 soundness ordinal is a measure of the pi12 consequences of the theory that are false. And the bigger it is, the closer that theory is to being pi12 sound. So if you take this one, the pi12 soundness ordinal of this theory would presumably be very big. And this takes us to the world of proof theoretic classification of theories. And we will first do this focusing on O12. And the intuition is going to be that the larger O12, the more correct the theory is. But you can say very precise results. So O12 of T is smaller than delta 12 if and only if T is not pi 12 sound. Where delta 12 is the supremum of lengths of delta 12 pre-well orderings on the natural numbers. And yeah, so the other intuition will be that ordinals with the theories with similar pi 12 soundness ordinal will have similar degrees of soundness. Let's say this is number one. Number two says O12 of T is equal to 0 if and only if O12 of T is smaller than the proof theoretic ordinal of T, if and only if T is not pi 11 sound. So maybe I'll make a drawing. We have here is delta 12, which for purposes of well, so this is saying that the O12 of the theory has to be either something small or it's infinity. So there's nothing happening here. Could be 0. And in fact, it is 0, provided that it's smaller than the pi 11 norm of the theory. And if T extends ACA 0, like all theories do, according to the rules of today, then so it could be here. Number 3 says O12 of T is recursive, so it's smaller than omega 1 ck if and only if T is not Boolean pi 11 sound. So if T proves a false Boolean combination of pi 11 sentences, then its pi 12 soundness ordinal will be recursive. So it'll be in this region. And so what's left? I guess what's left is this region right here. So actually it left so much more room than needed. Let's go back here. So here are all the theories according to their O12s. Here we have the pi 11 unsound theories. Here we have the theories that are pi 11 sound, but Boolean pi 11 unsound. Here we have the theories that are Boolean pi 11 sound, but pi 12 unsound. And here we have the pi12 sound theories. So this is what the world of soundness for pi12 looks like. And O12 is very well. It could be many things. It could be admissible. It could be not admissible. There are many things it couldn't be. For example, it can't be anything here. Can't be omega. Can't be omega squared. If it's not zero, it has to be at least epsilon zero. And in fact, you can show that it always has to be an epsilon number. So this is a lemma. O12 T is of the form epsilon alpha. So these are the ordinals, i.e. omega to the O12 of T is equal to O12 of T. Why? Because there is a theorem of, I believe it's due to Girard, which says that ACA0, or let's say over RCA0, ACA0 holds if and only if the function that maps x to omega to the x is a dilator. So this is called the exponential dilator. Well, I just said a function. So this equivalence is true if you just demand that well-foundedness is preserved. But you actually, if it is, you actually get that this is a dilator. So what is this dilator? Let me just say. Exponential of x, or exponential, is omega to the x. And if f is a function from alpha to beta, take some gamma less than alpha. So gamma can be written in Cantor normal form. This is for some k, some alpha 0 greater than equal to alpha 1. And all smaller than alpha. Then x of f will be a function from omega to the alpha to omega to the beta. Oh, sorry, this is the typo. Gamma is less than omega to the alpha, where gamma, as above, gets mapped to, you just shift the parameters. So this is the exponential functor, which is a dilator, and this fact is equivalent to ACA0. Oh, and why does the lemma follow? So suppose that the O12 of T is less than omega to the O12 of T. What does this mean? It means that there is a predilator T such that T proves D is a dilator. D of gamma is well-founded. Or let's say D of O12 of T is ill-founded. and O12 of T is least such. But then T proves that D is a dilator. T extends AC 0, so it proves that exponential is a dilator. So then T is going to prove that X composed with D is a dilator. So T is going to prove that what? Okay, let's derive something from this first. Observe that for every alpha is a fixed point of the exponential function if and only if alpha is of the form epsilon gamma for some gamma. That's the definition of epsilon gamma. And the epsilon numbers the sequence of epsilon gammas is generated by epsilon gamma plus 1. How do you get that? It's also the supremum of you take the previous one, and then you add 1, and then you take the omega exponential, and so on. And this is a continuous sequence. So that's how you generate all the epsilon numbers. You take the previous one, add 1, and then you apply infinitely many exponentials, you get the next epsilon number, and so on. And limits of epsilon numbers are epsilon numbers. So so we can find some gamma such that epsilon gamma is less than O12 of T, less than the next epsilon number. And thus, we can find some n such that omega n times epsilon gamma is less than or equal to O12 of T, less than omega n times plus 1, epsilon gamma plus 1. But then T will prove that the composition of dilators is a dilator. So we can take D, apply exponential n plus 1 times. And this is going to be a contradiction because exponential n plus 1 after D applied to epsilon gamma will be greater than O12 of T. And oh, I see. Let's do it the other way around. We apply D after exponential n plus 1 times. So D after exponential n plus 1 times, since this is bigger then O12 of t, this will embed into d of O12 of t. And so this is going to be ill-founded. Sorry, the other way around. This is going to embed here because O12 of t is smaller than exponential n plus 1 epsilon gamma. So we have some t-provable dilator, which becomes ill-founded at epsilon gamma. But this was supposed to be for which that happens. So this is a contradiction. This contradicts the definition of O12 of t. That's the proof. Okay, so that's the reason why. So what were we showing? We were showing that O12 of t is an epsilon number whenever t is an extension of ACA0. So any questions?
Excuse me. Could you explain what is the definition of delta 1, 2? Our students haven't learned this, so yeah, you can explain it. This delta 1, 2.
Yes, of course. So delta 1, 2, it's a, how do I do this? Interesting. There you go. Delta 1, 2 is the supremum of ordinals alpha, such that alpha is isomorphic to R for some delta 1, 2 relation R on the natural numbers. So that's it. So you look at all the delta 1, 2 relations. Some of these are well ordered, so they're going to be isomorphic to ordinals, and then you just look at their supremum. It's the least ordinal, which is not the order type of a delta 1, 2 well ordering of the natural numbers. That's it. So what this was saying is that's the limit of the O12s that are non-trivial. So looking at this drawing, maybe we can repeat the drawing. What's going to happen is it's going to look more like this. Here you have epsilon 0, epsilon 1, omega 1 ck, delta 1, 2. And we had this possibility here. And then it could be epsilon 0, epsilon 1. Could be a bunch of other things. And then here, it always has to be an epsilon number. So it's not a continuous spectrum. And so the next question is whether that's the right picture, whether every epsilon number can be realized as the spectrum of pi12 unsound theory. And I'll give you 20 seconds to think about it. Let me just get some more water.
Okay, the speaker will come back soon, so we can just take a short break. He will back soon.
Well,
Okay.
I'm back already. It was meant to be a really short break. So, shall we continue?
Yes, you can continue.
Okay, great. Well, maybe you had time to think about it, but the answer will gonna end up being no. But only in the non-recursive part. So for each well, maybe let me say more about that in a bit. But there's a reason why there should be gaps. And that's the following. Suppose alpha is 012 of t. And this is by some recursive predilator t. Then alpha satisfies t applied to the ordinals is ill-founded. So this is a sigma 1-1 sentence in the language of set theory. So this is the second order logic. And by definition, alpha is the least point where this happens. So L beta does not satisfy this sentence. Whenever beta is strictly smaller than alpha. So there is a sigma 1-1 sentence which holds in L alpha, but in no smaller L beta. And this is called alpha is not parameter-free sigma 1-1 reflecting. Or maybe we could say alpha is not sigma 1-1 definable. So there's a definition of alpha is a sigma 1-1 formula that holds at alpha, but not at any smaller ordinal. is saying that if alpha is the O12 of T, then alpha is definable, because there's a definition which says alpha satisfies this formula and no smaller ordinal satisfies it. That's the sigma 1,1 definition of alpha. So O12 of T is always sigma 1,1 definable. And not every ordinal is sigma 1,1 definable. And well, at the very least, because there are countably many formulas, so you can only have countably many sigma 1,1 definable ordinals. So now we have two restrictions O12 of T could be. One is that it has to be an epsilon number. The other one is that it has to be sigma 1,1 definable. And these gaps here are precisely groups of ordinals that are not sigma 1,1 definable. The least which is not sigma 1,1 definable is called lowercase sigma 1,1. So we have lemma. Suppose alpha is the O12 of T, then alpha is equal to omega to the alpha, and alpha is sigma 1,1 definable. And the question is whether that's the only restrictions we have. So whether this picture is correct. So we have the pi12 spectrum conjecture. Suppose alpha is equal to omega to the alpha, and alpha is sigma 1,1 definable. Then there is an RE extension T of ACA0 such that alpha is the O12 of T. And so what I wanted to do now was mention some results. Well, I'll mention a theorem first. So this is also joined with Fyodor Pakomov. So this is provable in ATR0. Suppose the pi12 spectrum conjecture fails, then second order arithmetic is consistent. So the failure of the pi1 conjecture consistency of second order arithmetic, which I think it's nice because it looks kind of unrelated. So that's the theorem. In particular, we know that the pi12 spectrum conjecture is consistent. With second order arithmetic. Because otherwise it yeah, so from now on we have about 20 minutes, so there are a couple of different routes we could take. I could say something about the proof of this theorem. I could talk about other results related to the conjecture and related to this drawing here. I could talk about related in a definition of 013 of theories and how that might lead to classification of theories. So what would you prefer?
I think you can decide.
Well, I mean, I don't care. I know all these things. So, but if nobody has any preference, well, this is your last chance.
Maybe
So
just,
if nobody has any preferences,
okay.
Oh, sorry.
Okay, maybe just the first one. Okay.
Oh, I forgot what the first one was. What was the first one?
Anyway, you can decide, okay?
Okay. Okay, so maybe I'll talk about this picture. Let's talk about the green part. So the green part So these were theories that are pi11 sound, but Boolean pi11 unsound. And here the theorem is that the pi12 spectrum conjecture holds for these theories. I call these theories of type B. So these are type A, B, C, D. And they, in some senses, behave more or less similarly, proof theoretically. So the pi12 spectrum conjecture for theories of type A is trivial. For type D, it's also trivial. So maybe type B and type C are the ones that are not trivial. But for type B, so the O12s of theories of type B are precisely all the epsilon numbers, which are sigma 1 definable and which are recursive. But I told you before that the least ordinal, which is not sigma 1 definable, is not recursive. Well, I told you it was called sigma 1, but this is not a recursive ordinal. So then what we have that the following are equivalent. Number 1 is alpha is the O12 of t for some t of type B. And number 2 is that alpha is an epsilon gamma for some recursive gamma. So remember, this means type B means pi11 sound, but Boolean pi11 unsound. So if I stated this as a conjecture and not as a theorem, it must mean that it's open for theories of type C. So let me tell you what I know about these. Type C means Boolean pi11 sound, but pi12 unsound. So here we have, suppose alpha is admissible. Then the pi12 spectrum conjecture holds for alpha. Thus, the following are equivalent for admissible alpha. 1 is that alpha is the O12 of t for some t type C. And 2 is that alpha is equal to omega to the alpha, and alpha is sigma 11 definable. So the only case that's open is theories of type C, which have inadmissible soundness ordinal. And yeah, these are strange theories. I don't really know. I don't really know what kind of things they can do. So since there is no time for proving any of these things, maybe instead I can just talk about something else. So what about pi13 and pi1n? And then we can do something similar here. And the first thing we have to do is define a suitable object to take the role of dilators. And this is an easy definition, which is given inductively on n. And 0 ticks is a well order. And n plus 1 ticks is a functor which goes from n ticks to well orders, which commutes with pullbacks and direct limits. So 1 ticks are dilators. And this was a natural generalization of dilators to higher type. And then we have the Jihad's theorem, which says the collection of reals coding m tykes is pi1 n plus 1 complete. So thus we can define the pi1 n norm of a theory as the least, well, n plus 1 is the least n ticks with respect to embeddability to which all the provable n tykes of the theory embed. And it exists provided that T is pi1 n plus 1 sound. And right, so you can prove more or less the same facts about it. What becomes more interesting is how to define the soundness classes. So now let's look at soundness classes. So definition, O13 of T is the set of all dilators such that P of D is well ordered for all P such that T proves that P is a tube ticks. So this is the analog of O12. O12 was an ordinal, but you can think of that ordinal as the set of all its predecessors. And you can think of the predecessors of O12 as being the good ordinals with respect to T. And so that's kind of the notion that will extend here. O13 will be the set of all good dilators with respect to T. And on anything inside of O13 of T, if we take a pi13 consequence of T, by completeness, that will be a statement saying that some recursive P is a tube ticks. These will go to ordinals, and then things outside will go to ill-founded orders. So this is kind of like the region where T is correct, where T is pi13 correct. And we don't know that much about O13 of T. This is a weird object, and it's very strange. I'd like to understand it more, but I know some things about it. So, for example, O13 of T doesn't even have to be closed under addition. So this is very strange. So you could have T1 in O13 of T. So T is pi13 sound on D. T2 is also in O13 of T. but D1 plus D2 is not in O13 of T. And well, this is weird because this is saying that the pi13 consequences of T are they're very strange. I don't know. These are weird theories, but they could exist. And this all has that as you look at higher and higher complexity, sentences, Lindenbaum algebra just become more and more complicated. So this is something you could have. And so the reason why it's hard to study this class, it's because you can't say much about it. Might not even be close under addition. It is closed under exponential though. So if D1 belongs to O13 of T, then the exponential of D1 also belongs to O13 of T. So you have that. And you can use this to, well, I mean, there's a classification question of what are the possible, so maybe I'll state this as a question. What sets of dilators can be of the form O13 of T? So this is the spectrum problem for I13. And well, I don't have any conjectures for this. We do have a partial answer. We have a classification of, or maybe a characterization is better to say, of the sets of the form O13 of T restricted to recursive dilators. So what are the possible sets of this form? And we have this in a paper called, what's it called? The spectrum of pi13 soundness. You can do with O13 is proof theoretic classification with O13. So you can have theorem the following are equivalent. O13 is empty if and only if T is pi11 unsound. You can have other results. O13 contains all recursive constant dilators if and only if T is Boolean pi11 sound. team, O1 team, O13 of T contains all recursive dilators if and only if T is 2 sound O13 contains all constant dilators if and only if T is pi12 sound, and so on. There are other types of results you can prove of this form. So the picture here is the following. Take picture, these are the ordinals. And here are the recursive dilators. And here are the delta 1,3 dilators. Let me copy this picture. And let's say assuming V is equal to L. So you can look at which dilators belong to O13 of T. If the picture looks kind of like this would be a T, which is sigma 1,2 sound. If the picture looks kind of like this, then this would be a T, which is pi12 sound. If the picture contains both those things, then this would be a T which is both sigma 1,2 sound and pi12 sound. And if it just contains everything, then, or if it contains all the delta 1,3 dilators, then it would be fully pi13 sound. Yeah, so that's the type of classification theorem you can get from O13. And yeah, so maybe this is a good point to stop and see if there are any questions.
Okay, let's first thank the speaker for this very deep lectures. Okay, yeah, I think this work is very technical, but also important. And the speaker and his research group develop an abstract framework to develop ordinal analysis to deal with the theorem with more higher complexity. So I think this work definitely is original, and yes, I think it's a big progress. But maybe you and some students and maybe have some knowledge gap. Maybe you do not understand the many, but I think it doesn't matter. But from his lecture, you can grasp his motivation for this work and the bigger pictures. Also, the big theorem he presented and the theorems he talked about, I think is very wonderful. You can see the nice picture of the classification prosthetic classification with 012 and 013. Okay, now is our feedback section. Okay, our audios are welcome to propose your questions. Okay, even if maybe your question is just about the definition of some notion, that is okay. Okay, be free to ask. Okay. Anyone? You can post your question in the chat box, or just raise your hand, or just open your video to ask. Both are okay.
Hello, can you hear me, Professor Chen?
Yes.
And Yuan,
please.
Thank you so much for your wonderful talk. Even though I'm not an expert in this field, but I have some questions. Maybe it is too naive for you, but I just want to know something more about it. After you get the result of the classification with 013, what's more consequences of this classification from perspective of proof theoretic view? Can you explain something more about it after this?
Yeah, good question. So, I mean, the interesting thing, which I thought was that there is some classification. So, because normally the paradigm in proof theory is that you always assume that the theories are pi11 sound, because then otherwise ordinal analysis tells you nothing, because then all the theories look the same, and then they just prove everything, and it's nonsense. You can't say anything about them. And it's kind of interesting that when you go look at pi12, pi13, there actually is something to say about theories that are not sound. And that was very surprising. And there's actually something interesting. They have like a nice structure. They have a deep structure. You can say things about them. You can ask questions. You can ask questions that are very, very precise questions, but don't have a clear answer, or not yet. So I think that's interesting. Also, the examples of theories you can come up with, especially when you look at higher complexity, they're very rich examples. So theories like ZFC plus V equals L, you could say that's a pi13 unsound theory.
Oh.
Well, maybe pi14 unsound theory. And well, I would say that. I don't know. It might not. Maybe some people might disagree. And the point is that there are theories that people work with that are examples of this, and then they have a nice structure. And yeah, so I don't have any application of these things. I have questions about these things. Maybe there is some use for them, or there will be, but not yet.
Okay. Another follow-up question. I'm not sure if you have already thought about it before. So I'm working on the structural proof theory. In fact, so I wonder if there's some relation between this result and structural proof theory.
Yes. So actually there is. Well, it depends on what you count as structural proof theory. But because all of these methods required working with infinitary proofs.
Yeah.
But they were with infinitary proofs in a careful way. So for example, in the proof of this theorem,
yes,
it involves, there are steps which involve, and in other proofs, but in this one in particular, there are steps which involve the manipulation of, you have this proof, and then you want to make sure that it's a cut-free proof, and then you want to know how long it is, even though it's an infinite proof. You really want to know how many steps it has, or what its rank is, and then you want to work with the rank. And also with also in this proof, that also involves working with infinitary proofs very carefully. And so for me, anything that, because normally in proof theory, you talk a lot about proofs and you want to know if there is a proof of something or if there is no proof of something. And you don't always care about what that proof is exactly.
Yes, exactly.
And anything that really involves working with the actual proof and checking its length, its properties, its rules, that sounds like structural proof theory to me.
Yeah. Thank you so much for your answer. Okay.
Yeah, thanks for the question. It's a nice question.
Okay, thank you, Professor Liang, for the questions. Any more questions? Anyone is welcome. Okay, I first ask some questions. Firstly, you show a great theory. We see that Pavan-2 spectrum conjecture, if it fails, and then second order arithmetic is consistent. Yeah, this is a wonderful theory. Yeah, but also you show that ordinals, for example, recursive ordinal and admissible ordinals, and this Pavan-2 spectrum conjecture holds. So my question is just, do you believe that the Pavan-2 spectrum conjecture holds? Do you believe that this conjecture fails? If it fails,
yeah, that's a good question. Actually, I used to think that it was true. That's why. And I think Fyodor also used to think that it was true. That's why that's the conjecture. But then I think we now think it's false. I think it's false. It's just not, the counterexample needs more than second order arithmetic. So I would guess that third order arithmetic can prove that the conjecture is false.
So is that we only need to find some counterexample for some non-recursive and inadmissible ordinal, right?
So I think that the point it's going to fail at some point, but that point has to be a really big ordinal, bigger than the ordinal of the smallest well-founded model of second order arithmetic. So I think it's going to fail at some point, but yeah, beyond the point where, like, if you go along L, you have to go past the first L alpha, which satisfies second order arithmetic before getting to the counterexample.
Okay.
But I don't know, maybe not. Maybe it's just true. I don't know.
Okay, another question. This theorem shows your analysis of Pavan-2 suddenly respect to the consistency problem. My question is that you know that the Ghent project of the conditional ordinal analysis is closely related to Hilbert's consistency problem. We can see that this is the motivation of the traditional ordinal analysis, and now for your now this more abstract framework toward ordinal analysis. What's the relationship with the Hilbert's consistency problem? For example, for this theorem, he shows the relationship about whether the consistent of second order arithmetic. So, what about the consistency problem of the fragment of the second order arithmetic?
Right. So that's surely part of the motivation. But I guess the observation was that Genson's result and work that comes after it not only gives you consistency of fragments of second order arithmetic, but it gives you pi11 correctness for free. And then, so you could try to extend this in 2 dimensions. One is increasing the complexity, and the other one is making the theory stronger. So you want to study theories that become stronger, not only in consistency strength, but in general consequences. So a theory like PA plus the consistency of ZFC is maybe not as interesting as ZFC itself, because ZFC gives you all these things that PA can't get just from consistency, because it's just a lower complexity thing. So yeah, it comes from that, but you have this extension in 2 different axes.
Okay. Yeah, my question is about the comparison between your approach and the traditional ordinal axis. So the traditional ordinal the main tool is just like a calculation of the inflammatory proof system and the ordinal representation. And for your this abstract framework, you use some abstract object, not ordinal, but some more abstract and complex objects like dilators. And for the work for your work about dilator, is there any some similar kind of things like ordinal representations system, this kind of thing?
Right. Yes. So actually, the dilator itself is an ordinal representation system. So there is something called Jehad's isomorphism theorem, which says that every dilator is isomorphic to an ordinal representation system.
Oh.
And so if you have a dilator like this, this is itself an ordinal representation system, but it's like a relativized ordinal representation system, because it's like you have an X, and then you feed it here, and then this becomes an ordinal representation system for epsilon X.
Mm-hmm.
So you can always show that if you take this proof theoretic pi12 norm and you apply it to 0, then you get the pi11 norm. And since this is a recursive object, this is given explicitly, so you obtain some explicit description of this object. And yeah, then the problem is to compute this thing. And depending on what T is, it might be easier or harder than computing this. But yeah, there is I didn't talk about that today, but there is a connection.
Okay. Maybe my last question is about Mitchell Ranson once also gave an online lecture at Wuhan University, and in the last part of the lecture, he talked about the current status of ordinal analysis, and he said that the current status is that we don't know the prosthetic ordinal for the serial pi13 comprehension. And my question is that whether you and your group this new approach toward ordinal axis. Anyway, how do you think of the status? Whether your new approach can, for example, can answer this upper problem for the traditional ordinal analysis for the pi13 comprehension?
Well, not yet. But I think this gives a promising tool that could lead to that eventually, but not yet.
You believe that this approach can be generalized to analyze any power n zero, right?
Yes.
Okay. That's very great. Very important and original and yeah, important project. Okay.
Yeah, thank you.
Okay. Any more questions? Let me see the time. Okay. Okay. Even no other question, but we also run out of time. Okay. Finally, let's thank the speaker again for this very interesting, deep, also at least frontier work of ordinary essays from a very young scholar. So even if we don't know too much about the technical detail, if you have interest, you can see his paper. But yeah, we enjoy the idea. At least we know that voice of frontier work in this very important field on essays in Pro Zero. Okay, also we thank our audience to attending this lecture. Okay, I think it's time to say goodbye. Okay, that's all for today's lecture. Okay, bye-bye.
Bye bye.
Thank you very much.